You look up at the night sky and see billions of twinkling stars. That is the universe you think you know. But what if I told you that 85% of the cosmos gives off absolutely no light whatsoever?
We live in a universe dominated by an invisible entity, something you cannot touch, and almost impossible to detect.
This mysterious entity is called dark matter. It is a physics riddle that has puzzled us for nearly a century. Our story begins with pioneers like the astronomer Vera Rubin.
According to Newtonian physics, stars on the outer edges of a galaxy should be rotating very slowly.
But Rubin discovered something shocking. The outermost stars were spinning as fast as, or faster than, the inner ones. An immense, unseen gravitational force was holding the entire galaxy together, preventing it from flying apart. This invisible stuff had to outweigh visible matter by 5 to 1. It forms a giant dark matter halo. All the stars and planets, including ourselves, are just a thin layer of paint on a massive, invisible canvas. The key characteristic: dark matter does not reflect, absorb, or emit light. It is completely invisible. Only 5% of the universe is made of the ordinary matter we know. Dark matter accounts for a staggering 27%. Right after the Big Bang, dark matter played a crucial role in distributing matter throughout the cosmos. Without this unseen gravitational glue, the ordinary matter wouldn't be massive enough to sustain the fast rotation.
The beautiful spiral galaxies we admire would simply be torn apart, their stars flown out into deep space.
In essence, dark matter provides the structural skeleton. It is the cosmic scaffolding upon which galaxies are built. It creates what we call the cosmic web, a gigantic structure of clustered galaxies and vast, empty voids.
Within this web, galaxies congregate in the regions where dark matter density is at its absolute highest.
Are you curious? This invisible dominance is precisely the reason that you and I exist here on Earth today. But if it's everywhere, flowing right through space, why can't we see it, feel it, or even measure it? Although we can't observe dark matter directly, we can clearly see and measure its powerful effects. Dark matter has mass, and mass creates gravity. Gravity, as Einstein showed, bends space-time. Light from very distant galaxies gets warped and bent as it passes through huge clusters of dark matter. This creates the effect of gravitational lensing, a strong visual proof of this unseen mass's presence. The most famous example is the Bullet Cluster, where two separate galaxy clusters violently collided. As they collided, the hot gas, ordinary matter, interacted and slowed down, accumulating in the center. But the dark matter, mapped via gravitational lensing, did not. It passed straight through without interaction. It was like a crash between two clouds of hot gas and two ghosts passing through each other, completely unscathed. The Bullet Cluster is direct physical evidence that dark matter has a distinct existence from ordinary matter. So, if it doesn't interact with light or ordinary matter, what is this elusive dark matter particle made of?
Scientists have proposed several different physics hypotheses regarding the true nature of these invisible particles.
The leading candidate is WIMPs, weakly interacting massive particles, which could explain many mysteries. WIMPs are theorized to be many times heavier than a proton, but they interact only via gravity and the weak nuclear force. Trillions of YMPs could be streaming through your body right this second, leaving absolutely no trace behind. A second major candidate is axions, super lightweight particles that interact with normal matter extremely feebly. Axions are thought to be so light that they behave more like an energy field or a wave than discrete particles. The hunt is for one of these two types: a heavy, fast-moving particle or a super lightweight, pervasive wave. To find them, we must build the most sensitive detectors, located deep underground to eliminate background noise. Dark matter detection labs are placed far below the surface of the Earth, shielded from cosmic radiation. The detectors contain super pure, cold liquids, like xenon, shielded from virtually all external noise and interference. The hope is that one WIMP particle will occasionally collide with a xenon nucleus, creating a tiny, measurable flash of light. Yet, so far, these cutting-edge detectors have recorded no clear, unequivocal signal of the particle's existence. difficulty is immense. Searching for dark matter is like trying to hear a single whisper in the middle of a massive stadium.
This persistent silence is forcing scientists to re-examine a fundamental question. Have we misunderstood dark matter entirely?
If WIMPs and axions are not the answer, perhaps we must entertain an even more mind-bending possibility.
One alternative hypothesis is MOND, modified Newtonian dynamics. This proposition is truly radical.
MOND suggests that we don't need dark matter, we just need to alter the laws of gravity at extremely low accelerations. Surprisingly, MOND does a good job of explaining the unusual fast rotation curves of many spiral galaxies.
However, MOND fails when trying to account for much larger scale observations, like gravitational lensing or the bullet cluster.
Whatever the ultimate answer is, it is clear that something is profoundly missing from our current understanding of the universe.
Another compelling hypothesis being considered is self-interacting dark matter. This sounds inherently strange.
SIDM particles interact with each other. They collide internally, but they rarely interact with ordinary matter. SIDM solves some nagging problems regarding the overly dense concentration of dark matter predicted by older models. A third idea is warm dark matter, WDM, particles that move slower than light but faster than the traditional WMs. WDM helps explain the observed deficit of small, satellite galaxies that the cold dark matter model predicted.
Perhaps dark matter is not just one particle. It could be a complex ecosystem composed of multiple different types of particles.
Some theories even propose the existence of a dark force, a completely new force that only acts upon dark matter.
This dark force would have its own carrier particle, possibly a dark photon, which is invisible to our current instruments.
All these hypotheses and indirect evidence point to one simple truth. We are only seeing 5% of the cosmic iceberg. Finding dark matter is not just a scientific discovery. It is the essential key to unlocking the remaining 95% of the universe.
The stark reality is, we still know virtually nothing about 85% of the material that surrounds and shapes our existence.
The hunt for dark matter isn't only taking place deep underground, but also inside massive particle accelerators. At CERN, the Large Hadron Collider is smashing particles together at incredibly high energies.
Physicists hope they might be able to create dark matter particles right there in the lab during these collisions.
Detecting dark matter this way involves looking for unaccounted for energy that is missing after a collision takes place.
If the total input energy is greater than the measured output energy, that deficit could be the telltale signature of dark matter.
A philosophical question arises. Does dark matter affect our lives in subtle ways that we have yet to recognize? As the solar system moves through denser regions of dark matter within the Milky Way, could anything be happening?
Some scientists hypothesize that dark matter could accumulate in the Earth's core, generating small amounts of heat.
This is just an example of the minuscule, almost undetectable physical interactions that could potentially be taking place.
In the future, new generations of space telescopes will map the distribution of dark matter with unprecedented detail. Missions like Euclid and the James Webb Telescope will help us see its gravitational effects more clearly than ever before.
The search for dark matter is arguably the greatest ongoing scientific quest of the 21st century. Whenever we find it, whether it's a new particle, a new force, or a change to gravity, it will instantly rewrite physics textbooks.
It is a massive global effort, unifying the fields of astronomy, particle physics, and computer science. Dark matter is not a mistake in the math. It is an essential and fundamental component of the cosmos.
It serves as a profound reminder that the universe's greatest mysteries are often the things that we simply cannot see.
The universe is governed by an invisible ghost, and the story of the missing 85%